Hello everybody, this is Dr. Dave with Physics 152, and I wanted to give you a quick overview on Faraday's Law, Lenz's Law, and the Lorentz Force. These topics are considered by some the most challenging issues that we come up with in Physics 152, so I want to try to make some sense of that. So Faraday's Law is essentially a statement that a changing magnetic field produces an electric field. All right, so what does that mean? If you had some kind of bar magnet, some north-south magnet, and you were to move, say, that magnet around, right? So, here's my north-south magnet, and I were to take that magnet and move it around. What am I doing? I'm taking the magnetic field lines that come out of the north and back into the south, right? And when I'm moving it around, what am I doing? I'm changing the magnetic field that any point in space feels, right? So if I move this around, I'm changing the field at that point as I move my magnet. So as it turns out, in the wake of kind of that magnetic field, you're producing an electric field. And so what we want to understand is the following. If you have free charges at a location in which one of these electric fields is created, what does free mean, like a conductor or something like that, then those charges are free to move, and they will. And they'll move in such a way that it produces a current. Lenz's law is a statement about what direction ultimately that current will be through the magnetic field. So Lenz's law is a way of telling us what kind of current will get produced, more specifically in a way that will oppose the change. And then the Lorentz force, which we've actually already seen, we just didn't really focus on that label. The Lorentz force is just FQE plus QV cross B. So what is this? This is just the combination of your electric force and your magnetic force. However, in what we're going to be looking at today, we're not thinking about a static external electric field. We're only going to be focusing on this part of the force. So why don't we experience this in real life? Why don't we encounter it? The simple answer is that we don't normally see this because the effect is quite small. On your PhET simulation, you should have seen that unless you move the magnet in just the right way around the coil, you didn't produce that much magnetic field, or I'm sorry, that much electric field, and you saw that by not producing a ton of current. So, understanding Lenz's law. Let's look at this first from a Lorentz force point of view. What do I mean by that? Let's imagine you have a metal conducting bar, right? So this is like, took a paper clip or something, I made a U-shape out of it. And then I take another conducting piece and I set it on top. Now I put it in a uniform magnetic field. Now I don't need to draw all of these B field vectors, but I am, because I want to be really clear, I'm saying that throughout this entire region, there is a uniform field. Now, technically, the field outside of this doesn't matter at all for what we're doing, but I just want to be clear about what's going on. And so I have another conducting thing here. So now when I take this bar and I move it to the left with some velocity v, we're going to ask the question, does this produce a force? Well, think about it. What's going on in here? Remember, for current, we talk about the motion of positive charges. Even though in reality we know that it's negative charges that are moving, we're going to just pretend current is always positive charges, and that's going to be our focus. So if I have a hypothetical positive charge sitting on this bar, and I find myself moving, well, what am I going to experience, right? This is right-hand rule. Now I'm going to have a V and a B downward. And so in that right-hand rule, V cross B is going to push this way, right? If you don't see that, stop for a minute, pause the video, think about what you know about that. V cross B is going to be downwards. Since it's a positive charge, V cross B is going to lead to a positive force. And that's going to push charges this way, which is going to start a current going that way. And with this current, it's then going to flow around here. So what does that mean? Well, now I'm going to create what I call an induced current flowing this way around my wire. Okay? And so that induced current is also going to create its own induced magnetic field. So from the right-hand rule again, what we're going to get is an induced B field that's into the page. All right, so that's just our understanding from the Lorentz force. Now let's look at it from Faraday's law, Lenz's law point of view. All right, so what we want to see here is the following. I am now changing the amount of magnetic flux that goes through this area. All right, how am I doing that? I'm taking this area and shrinking it, right? As I move this to the left, I'm shrinking that area and I'm changing the flux. So flux is our new concept, right? Flux is BA cosine of theta. And in this case, the external field is into the page. And we're going to choose, it turns out you can always choose the area vector to be the way you want as long as it's perpendicular. So we could have chosen area in, or we could have chosen area out. It wouldn't have actually made any difference. As with potential, what really matters is the difference from that. So if you had wanted and said that the area vector was pointing outward, you could have made this theta 180 degrees, and it wouldn't change any of our answers so far. So from a flux point of view, we have decreasing flux as this bar moves. And we have decreasing flux, and Lenz's law is going to oppose that decreasing flux, meaning that it's going to want to create a current that produces more magnetic field to restore the loss that's happening. If I was moving this way, I'd be getting more flux, and the induced field would then oppose that. So because I'm shrinking my loop, I'm going to get an induced magnetic field, so I'm going to write B induced this way, to try to compensate for that loss of flux through that loop. And so what we look at here is we say, okay, flux is BA cos theta. The derivative of that flux with respect to time is going to give me a product of the derivative of BA, but B external is held constant. It's just the area that's changing. So then B external is now going to be just the derivative of area. What's my area? It's my x times my y coordinate. So here I've got my x times my y coordinate. The y coordinate isn't changing, only the x coordinate is, so we're left with a dx dt, which is, of course, from physics 150, just our velocity. So then what we say is the change of flux with respect to time is Vy B external. Now, again, Lenz's law is saying that the EMF that's produced within this loop opposes, that's what the minus sign is, it opposes that change of flux. So this is why we're saying B induced is going to be into the page. So B induced is going to go into the page so that we get more field through the coil to compensate for the loss of field through the coil from the closing area. And once you do a few of these problems, it does start to make more sense. But this is kind of 2 points of view on why this is happening, right? From a Lorentz point of view, we can see that the moving charges experience a force, which produces a current, which then opposes. From a Faraday's law, Lenz's law point of view, we can see that there's an EMF produced in here that's going to drive a current in the same direction as you did here, and the Lenz's law is opposing that loss of flux. All right, so let's move on to a rotating coil. Now I'm going to admit that this one is pretty tricky, largely because of perspective. All right, it's really challenging to see three-dimensional shapes in a two-dimensional context, especially when you can't see me holding an object and changing it just a little bit. So what we're thinking of here is the following. We have a square coil, and that square coil is going to come up on this side and down on this side so that it's rotating around this way. So if I were to just look at it from this point of view, I would see a flat coil with this side going up and that side going down. If I were instead going to look straight down from above, this is what I would see. I would see this side going up and this side going down. And so we're going to have a B external again here, and in this case our B external is going to be into the page. All right, so from a force point of view, what kind of current do we think is going to get created here? If I think about it from a QVB kind of perspective. Well, here I get kind of this weird thing. I've got the magnetic field going down, and on the right-hand side, my velocity right is going up. Well, the force is QVB sine theta. Well, what's theta? Theta is 180 degrees. Sine of 180, as you know, is 0. So I have no force here. So in that case, it would seem to be that I don't have any current right now. Let's look at the other side. On the other side, what do we have? We have the velocity down, the B field down. So that's an angle of 0 degrees. Sine of 0 is 0. So again, it looks like there's no force here, no force here. Now you could ask what's happening on the sides here, right? We're not going to, other than just to say, imagine each point of the side is either going to be coming up or going down, right? Depending on which side of the turn they are. So there's going to be no current at this moment. That might seem weird, but it turns out that's exactly what Faraday's law says as well. We'll understand that more in a minute. So now what I want to think about is this coil starts here, and now it's rotated to here, and now it's rotated all the way to the top. And that's what this side view is showing. So the external B field is still pointing downward. Our coil is oriented straight up and down. And at this point, this part here is right here. and it's moving to the left. And this part here on the bottom is moving to the right. And so now the question is, what forces do we feel? So pause the video for a moment. Don't look at my answer. Try to do this yourself. Maybe cover up your hand, whatever. Really think about this. You know this is what we're going to ask you during the oral, right? Why? Because it's the hard stuff, right? That's what we want to know. Do you understand how to actually do this stuff? So pause the video, take a moment and think about it. All right, thank you for doing that. Hopefully we're going to agree on the answers. So we can ask ourselves, what force would a hypothetical charge experience that's in the sort of top part of the wire here, right? So that's this part right here, okay? So now we're going to velocity this way and a B field down. So by the right-hand rule, we're going to get a force coming out in that direction, right? That's what we're going to see here. So we're going to feel a V cross B coming out of the page. And at the bottom, we're going to see a V cross B going into the page. And again, because we're thinking about our sort of hypothetical positive current particle, then this is going to lead to a current, all right? And so if I then take another side view here and look at it, from this point of view, what we see is the top is going inward, like this was going inward here, and that's creating this flow of current, which is the same as this current here. So what we're going to get is, in this point of view, we're going to get a current that goes in a counterclockwise perspective. Now, why is that? What the heck is going on? Well, we have to think about it from a flux point of view. So how much field is changing when I'm at this position? And you can figure this out. Hold up a sheet of paper, look at it until the paper, imagine like a line going from your nose straight to the paper, and make that perpendicular to the paper. As you turn the paper a little bit about the center, the paper doesn't look any different, right? Not much, not until you get kind of a large angle. And so what that means is the flux isn't changing very much. And so if the flux isn't changing very much, that's going to be a smaller EMF. If that's a small EMF, that's going to be a small current. And it turns out that current is exactly zero at that orientation. So now take that same sheet of paper and hold it so that you can't see it, right? It's as thin or narrow as can possibly be. Now turn that paper just a little bit, and now you're going to see a whole lot of paper very quickly. So in that point of view, the flux is changing very fast. And when the flux is changing very fast, you're going to get a lot of current very quickly. And so the orientation of the coil relative to the field dramatically changes how much current you're going to get. So let's look at that a little bit more carefully. So as I said, what about the flux? So flux is BA cos theta. We're going to take the derivative of that with respect to time. We're going to note that the external B field is being held constant. We're also going to note that the area of this isn't changing. So our derivative is not going to touch the B field. It's not going to touch the area. It's only going to be of the cosine. So that's going to, of course, be derivative of cosine is minus sine. And then it's going to take the derivative of the inside, d phi dt. And so what is d phi dt? D phi dt is going to be the rotational rate. So it's, what is the rotational rate that you're going around sort of that pivot point, all right? So you sort of get this object here moving at what rotational rate. So if we write that out again, we get this minus BA sine theta. Well, sine theta, again, remember theta is the angle between the area vector and the field vector. So if we come back to this point and we just sort of start our area vector in alignment with our B field, then if our area vector here is our B field is here, that angle is 0. So then that says that the derivative of flux with respect to time is going to be 0 again, right? That's the EMF. The EMF is that negative change of flux there. So it says the EMF is going to be 0 when the B field and the area vector are aligned in that change. And again, because we're not changing the area, we're not changing the B field, we're only rotating. And so it says no current. This is going to agree with our force interpretation. Now again, what if we're at sort of this big angle? So again, this is where when you're looking at your paper, you can see only just the narrowest width of it. And as you turn it, all of a sudden the whole paper comes into view very quickly. So that change in flux is quite large. So now we're looking at the coil here. It's rotating upwards like this. So what's happening, our flux that is going through it is decreasing, right? Why? Because the flux through the loop will be 0 when it reaches here. So as it's climbing up, the flux is dropping. And so what we know from Lenz's law is that we want to induce a magnetic field that's going to oppose that drop. Now, I'm going to say, okay, the B induced through the coil is going to be this way. which you might be confused by. You might say, why isn't B induced going to be in that downward direction? And that's a perfectly reasonable question. What we know is the following. The induced B field is going to be coming through this loop in some way, whatever its orientation. It's going to come through that loop in some way so that it adds flux to the problem. But how is the B induced going to get created? The B induced is going to get created because of current flowing, right? So if current is flowing through this coil, it's going to create a field coming out of the center. So that field has to be perpendicular at the center of the ring to the loop itself. So yes, I would like the B field to just be that way, but I don't have a choice. It's got to be that way instead. So the big takeaway point is the following. When you have a changing flux and a conductor, you're going to create a magnetic field that opposes that change. And then once you know the direction of that opposed change, you can, from the right-hand rule, figure out which way your current had to have been. There's a lot of things to keep straight here. Please ask questions. Please talk to us. Please learn this material this week. Don't try to wait a couple weeks to get it. And we'll just cover this example again really quick here. If I'm dragging this object backwards, I'm increasing my flux. So I'd want to create a magnetic field to oppose that increase, which would be, in this case, it's going to be out of the page. If I'm moving my loop this way, I'm decreasing the flux. So I'm going to induce a magnetic field that's going to oppose that loss and go into the page. Don't try to memorize each situation. There are too many, and you know that when we change it just a little bit, you get kind of thrown off. Really think about what's the logic and wisdom here of happening. Thank you so much. Please ask questions.